We're going to look today at some examples on how to determine the electron domain geometry, molecular geometry, polarity, and hybridization of some molecules. So the first molecule we're going to look at is PCl3. Now the first thing, in order to determine all this information about the molecule, is to draw the Lewis structure. So what I'm going to do is first of all determine how many valence electrons I have. Now I have one phosphorus, has 5 valence electrons, so that's a total of 5, and then I have 3 chlorine, each with 7 electrons, so that's a total of 21. So I have a total of 26 valence electrons. I'm going to draw a tentative structure for my molecule, so I'm going to place the phosphorus in the center and the chlorine bonded to it. Now when I draw this tentative structure, I drew 3 bonds. Each bond is 2 electrons, hence I already placed 2, 4, 6 electrons in my structure. Therefore, I'm going to subtract them from the total and I'm left with 20. Then I'm going to fill and complete the octets of the bonded electrons. So I'm going to place 6 electrons on each of these chlorine atoms. And when I do this, I place a total of 18 electrons. So I'm going to subtract this, and I'm going to be left with 2. Now I have 2 electrons left. I'm going to place them on the central atom. So that is my complete Lewis structure. All my atoms have a complete octet. I want to verify that the phosphorus will not expand this octet in this structure. So I'm going to calculate the formal charge for the phosphorus, which is total of 5 valence electrons minus the total electrons in the bonds, which is 6 divided by 2. And then I'm going to sum up the 2 electrons in the lone pair, and it gives me a 0. So because the formal charge is 0, this phosphorus will not expand this octet, so the structure is complete. Now I'm going to count the number of electron domains I have around the phosphorus, and that's going to be 1, 2, 3, so each bond is an electron domain, and then the lone pair is another electron domain. So I have a total of 4 electron domains. Now, to determine the molecular geometry and the electron domain geometry, I'm going to use a VSCPR table. And I have it here, and I can see that I'm going to locate the number of electron domains. Notice that sometimes they're called electron dense areas. They're the same thing. So it's 4 electron domains. So the electron pair geometry or electron domain geometry is going to be tetrahedral. Now for the molecular geometry, I'm going to find it in this area of the chart. And what I want to do is go to my 1 lone pair, and then I'm going to cross where 4 electron domains, and I'm going to find trigonal pyramidal. So electron domain geometry is tetrahedral, and molecular geometry is trigonal pyramidal. For the bond polarity, what I want to determine is the difference in electronegativity to discover is the PCl bond is polar. So PCl bond, okay. And so I'm going to look at a table such as this one. I'm going to look at my electronegativity values, and I can see the difference is 0.8. That's more than 0.5, so this bond is polar. And for the molecular polarity, I'm going to have to reason this. I know that each bond, okay, will, because it's polar, will generate a dipole moment. This will cancel out if there wasn't a lone pair. But because there is the lone pair, this is going to create an asymmetry in the molecule so that these dipole moments will not cancel out. So the molecular polarity will be yes. So the molecule is polar. The last thing is the hybridization, where I can see I have one central atom that needs 1, 2, 3, 4 electron domains. You see I'm going to use again the same information. And then because I need the 4 electron domains, I need 4 hybrid orbitals. And I know I can have one s orbital, and then I can have up to 3 p orbitals. So this is a total of 4. So that's as many as I need. So the hybridization is sp3 for the central atom. Silicon tetrafluoride. Now, if I have silicon tetrafluoride, I have to, well, first of all, count the number of valence electrons because I need to do my Lewis structure. So silicon, there's one with 4 valence electrons, so that's 4. And fluorine, there's 4, each with 7 valence electrons, that's 28. So the total is 32. Now I'm going to do my tentative structure, and so I'm going to place it like this, which means I used 2, 4, 6, 8 electrons. So I'm going to subtract them here, and I'm left with 24. Now I'm going to complete the octet of the bonded atoms. Those are the fluorines. So I'm going to place 6 electrons on each fluorine. And because there are 4 fluorine, I used a lot of 24 electrons. I'm left with 0. Now, is this structure complete? Yes, because I have each atom with a complete octet, and the formal charge on silicon will be 4 minus 8 electrons in the bonds divided by 2. I have no lone pair, so that will give me 0. So the formal charge on silicon is 0. It will not expand its octet. Now I need to count the number of electron domains, and that's 1, 2, 3, 4. So I have 4 electron domains. So the electron domain geometry, like before, is going to be tetrahedral, but in this case, I do not have any lone pair. So the electron domain geometry and the molecular geometry are going to be both tetrahedral. And you see that if you do not have lone pairs on the central atom, the electron domain geometry and the molecular geometry are always going to be the same. Now, polarity of the bonds. On my table, I can find my silicon, and then I can find my phosphorus, and I can see that the bond is definitely polar. In this case, I have a symmetrical structure where these dipole moments are all in opposite directions, so they will cancel each other. So bond polarity is yes, molecular polarity is going to be no, because they cancel each other. Hybridization, I need 4, because I have 4 electron domains, I need 4 hybrid orbitals, so the hybridization of the central atom is sp3. Okay, let's look at the last example that I wanted to go over today, and that's BRF5. Now, likewise before, I'm going to do the first thing, I'm going to do the Lewis structure. So bromine, there's 1 and has 7, so it's 7 electron. And then I have fluorine, there's 5 times 7, so it's 35, so the total is 42. Now I'm going to place bromine in the center, and I'm going to form 5 bonds to place my 5 fluorine. You see that bromine has an expanded octet already, but it can do that, and so now I placed 2, 4, 6, 8, 10 electrons. So I'm left with 32. I'm going to place 2, 6, 4, 6 electrons on each fluorine to complete their octet, and this will give me 30. So I'm going to subtract the 30. I'm going to be left with 2. I'm going to plus the 2 on the bromine. So the bromine had an expanded octet to start with. It is expanding it further to accommodate the last 2 electrons. Formal charge on fluorine will be 7 minus 1, 2, 3, 4, 5, 6, 7. So the formal charge on bromine is 0. You can see how you can do formal charges quite quickly just by counting 1 electron per each bond, and then 1 electron per each dot. Having said that, I want to determine the molecular geometry and the electron domain geometry. Now, first I need to count the electron domains, which are 1, 2, 3, 4, 5, 6. And if I have 6 electron domains, I need to go in this part of the chart. So the electron domain geometry is octahedral. I have 1 lone pair, so my molecular geometry is going to be square pyramidal. Bond polarity. Now this is going to be given by the values here. So I look at my chart. So I got bromine and fluorine, and you see the difference is definitely more than 0.5. So these bonds are polar, yes. And you can see that most of the time, if you have atoms that are different, the vast majority of the bonds are polar, with few exceptions. And then molecular polarity, I have a lone pair, just one, on the central atom. So this is, I'm balancing my dipole moments, which will not cancel each other out, and so this molecule is going to be polar. Now, in terms of hybridization of the central atom, we said I can maximum use 1s, 3p, and 2ds. Now, I have 1, 2, 3, 4, 5, 6. So I need 6. So 1 plus 3 plus 2. So I'm going to use them all. So this is my hybridization of the central atom.